begin our study under acid-base equilibrium. So before we could actually get anywhere, we need to understand what an acid is and what a base is. So under the study of each topic, we have two definitions of each. So there's a guy called Arrhenius, and then there's also another guy called Brotsted. I don't even know how to pronounce this, but kind of something Brotsted, Lorry, something like that. So of course Arrhenius is double A. So according to Arrhenius, I think this is a definition we're actually familiar with. So an acid is defined to be a substance that when dissolved in water will basically increase the concentration of hydrogen ions. So an acid is a substance when dissolved in water. So the key point there is dissolved in water. So when dissolved in water, it increases the hydrogen ions concentration. Okay, so when dissolved. So that's the definition of an Arrhenius acid. An Arrhenius base, on the other hand, is actually defined to be a substance when dissolved in water or increase hydroxide ion concentration. So just in case you need the spelling, so it's hydroxide ion concentration in the solution. So Arrhenius, in summary, defines an acid to be any substance that increases hydrogen ions when dissolved in water. A base increases hydroxide ions. That's easy to remember, right? It's actually easy to remember because you know that examples of bases have hydroxide attached to them, and then acids have got hydrogens attached to them. So that's the one easy way of remembering what it can increase in a solution. And then Brotsted Lodi, on the other hand, defines an acid to be a proton donor, which in other terms to me makes no sense. Proton donor, and then a base to be proton acceptor. So you understand all these more in detail. So a proton donor, in that if you dissolve, for example, the hydrogen chloride or the hydrochloric acid in water, it's going to be separated from the chlorine, yes, meaning that you have chloride and hydrogen. So meaning that the acid by definition has donated a proton. Okay, then the proton acceptor, of course, anything that can come to attach to that hydrogen ion there. Okay, let me not complicate things, but these are the definitions of acids and bases according to Arrhenius and Brotsted. Yeah, we'll look at examples as we proceed. Okay, let's proceed and just talk about the aspect of looking at, first of all, start by looking at the examples of everything we've talked about. So examples of acids, we have hydrochloric acid, we have nitric acid. So one thing that you see about these acids is they have hydrogen attached to them. So we also have sulfuric acid, we have that other acid, I don't know the name. And then of course hydroxides, we have different ones, the ones that are made of metals from group 1, like lithium oxide, sodium hydroxide, and then we can get a few from group 2 as well, calcium hydroxide, barium hydroxide. So the ones that are attached to the hydroxides, these ones are the bases. The ones just attached to hydrogens, those are the acids. And of course most of these are strong acids and bases. Okay, so by definition we said, according to Arrhenius, an acid is a proton, not actually, that is Brotsted. So and Arrhenius said it increases the concentration of hydrogen ions in in the concentration. Let me give you an example. So if you have HCl, if it is dissolved in water, what is going to produce is there will be the proton from the acid, and then there will be the chloride ion, and then you're also going to have water. Okay, so this is the definition of an acid: any substance that increases the hydrogen concentration or the hydrogen ions concentration when dissolved in water. So in other terms, if you combine the hydrogen ion and the water there, you are going to have H3O positive. So this is what is known as the hydronium ion. So if somebody defines an acid to be anything that increases the hydronium ion concentration or hydrogen ion, they mean one and the same thing. So in a case where they ask you to write an equation involving water, you need to actually combine the hydrogen ion and water, so that you only have the hydronium ion together with a chloride ion in such a case. Okay. In a case where you're only talking about the dissociation of an acid separately, that's where the definition of only hydrogen ions comes in. It's basically one and the same thing. All we are just is combining water in a case where you are dissolving it in water to produce the hydronium ions. So hydronium ions are produced when an acid dissolves in water as well. Okay, I thought I needed to mention that. Now, one thing that you also need to notice is water has got the capability actually of even reacting again with bases. So just like I've given an example of a reaction with an acid, it can also react with a base like the one I've written there. So that is a weak base. So even what I'm putting here, by the way, this distinguishes weak and strong, whether we're talking about acids and bases. So this one is a weak base. So if I was to talk about sodium hydroxide, which is a strong base, we only are supposed to use a single one-sided arrow to show that it's complete dissociation. Okay, so by definition we said a base is what? Increases the hydroxide concentration. In other terms, from Brotsted we said it's a proton acceptor. So a proton in this case is the hydrogen ion. So NH3 is supposed to gain an extra proton, so it becomes NH4. So we have a positive there. So that positive indicates we've gained an extra hydrogen. Now, where is it coming from? It's coming from water. So water has lost an hydrogen, so it will only have OH, becoming now an hydroxide. So that's what happens for a base, and this is what distinguishes a base from an acid. So we've seen that a base gains, right? A base gains, and then we've seen that an acid donates. So in this case, by the way, water can be referred to as an acid in this equation. Water is an acid. Why? Because it has donated a hydrogen, and then NH3 is a base because it has gained, it has accepted a proton. Okay, so I can take this actually a chance to explain what conjugate bases and conjugate acids are. So NH4, when I'm using these arrows there, they show that there's a possibility of going back this side, meaning that whatever is on the right can react back to give us what is on the left. Okay, so if you consider a backward reaction, one thing that you're going to notice is the NH4 and the OHI. The NH4 is going to be the one donating, so we call it's a conjugate acid because it is the one that's capable of donating. It worked as an acid in the backward reaction. The hydroxide is definitely a base, so we're going to call it the conjugate base because it is obviously the one that's going to accept a proton in the backward reaction. So in other terms, the base becomes a conjugate acid on the right hand side, and then the acid becomes a conjugate base. I hope you get that. So don't get confused when they ask you to identify what a conjugate acid and a base is in a given equation or reaction. So remember I've said water can act as both as an acid as well as a base. So water is referred to as antiprotic. So it is referred to as antiprotic because it is able to act as an acid as well as act as a base. Okay. The other term is amphoteric. Amphoteric means water is able to exhibit both the acidic and the basic properties. Okay. So there's a difference there. Acting as an acid and a base, and then also exhibiting properties of an acid and a base is amphoteric. Okay. So let's proceed and just now get to look at the difference between strong acids and weak acids and strong bases and weak bases before we talk about the autoionization of water. Okay, so I know we're supposed to talk about strong acids and weak acids, and that's what we're going to talk about. So as a good practice as a student in chemistry, I would advise you each time you are learning, you practice questions. So since we already talked about conjugate acids, bases, definitions of Arrhenius, Brotsted, Lolly, yours is now to practice. Try to ensure you're able to remember all that. If possible, try to write them down. Okay. So look at this equation I've written there. Try to identify the conjugate acids, bases, and then if you look at what is happening on the left hand side, which one do you think is an acid? Is it water or the HCN? Okay, so I believe you've answered that. So if you look at that, I don't know whether it's an acid or a base, but if I check what has happened to it, it has lost a hydrogen, meaning that it has donated. So it's a proton donor. So that is already an acid. So it's an acid. Okay. So it's an acid. So therefore water is a base. Water is accepting the proton. That's why it has now become the anhydronium ion there. So therefore the hydronium ion is a conjugate acid, because in the backward reaction obviously we expect it to be the one donating, and then the Cn there is now the conjugate base. It's the one that will gain in the backward reaction. Actually, this is where the idea of now acid base equilibrium basically happens. Equilibrium, we are talking about the rate of the forward and the backward reaction getting to be equal. So this only occurs when you're dealing with weak acids and weak bases. It doesn't happen when you're dealing with strong acids. Okay, let's get to talk about now the difference between strong acids, weak acids. So I've already mentioned to say what makes a strong acid or a strong base is the fact that strong acids, they dissociate completely or ionize completely. By that we mean that if you dissolve, for example, HCl as a strong acid, of course acids are in aqueous state, if you dissolve it in water, it is going to ionize completely. By that we mean it is going to be ensured that every part of it is converted to the hydrogen and the chloride ions. You know that what is making up the hydrochloric acid is hydrogen ion and the chloride ion. So they will completely separate from one another or from each other. That's what makes it complete dissociation. So we use that full arrow, one-sided arrow, to show that it is complete dissociation. So some of you are wondering, of course I've already explained where the hydronium ion is coming from. It's just a combination of this hydrogen ion and the water molecule. Okay. Now when you talk about a weak acid on the other hand, when you talk about a weak acid does not dissociate completely. Only a fraction of it will ionize. So of course we can give an example of hydrogen fluoride. When you get to dissolve it in water, so the differences we use those kind of arrows there, and then of course there will be production of hydronium ion is still an acid, and then the fluoride ion as well. Now this is what distinguishes strong and weak. But to picture this in solutions, I think it will make more sense. So let's have the strong acid. So for a strong acid, if you dissolve HCl, you expect that HCl will produce a hydrogen ion and the chloride ion. Of course, you know that in the actual sense, if you have water, the hydrogen ion will be the hydronium ion, right? Okay, now for the demonstration, I'll take it as hydrogen ions. So in the solution there, you're going to have hydrogen ions and chloride ions alone only. Now on the other side, where we have a weak one, hydrogen fluoride, there what you're going to expect is, of course, beginning with the arrows there. I'm wrong. So what you need to expect on the other side is, since it is showing that we have the backward reaction and the forward reaction, in the solution only part of this has dissociated, meaning that you're going to have hydrogen ions, fluoride ions, and then the hydrogen fluoride itself as an acid will still be present in the solution. That's what this means. That's what it means. Okay, I believe that's now the clear demonstration of what distinguishes a weak acid and a strong acid. So the same applies to the bases as well. Take the same approach. Okay, so talking about the concept of autoionization of water, it is not something new to you, because if you've watched the earlier sessions or earlier videos, we've actually talked about water being amphiprotic, meaning that it's able to act both as an acid and a base. I also said water is amphoteric in that it's able to possess the basic and acidic properties. Okay, so water can act as both as an acid and as a base. So that is what is referred to as auto ionization. Now water, the funny part is water can actually react with itself. Surprisingly, since it's able to act as an acid and a base. I think I demonstrated that. Of course, let me give you the examples back. In a case where we have water reacting with a base like that one there, we expect that water will actually act as an acid. So we have NH4 forming there. It has gained a proton from water, and then we have production of hydroxide. So water in this case becomes an acid. In another case we can consider is a case where we have an acid, so hydrogen fluoride for example, then you have water. So in this case you expect that you have a production of hydronium ion and then also fluoride ion. So in this case water has acted as a base because it has gained a proton from the acid there. So this is the already indication that water is able to act as both as an acid and a base depending on what it is being reacted with. If you add a base to water, water acts as an acid. If you add an acid to water, it acts as a base. Okay, so that understanding, it is then also possible that water can actually react with itself, okay, to produce both the hydroxide and the hydronium ion. Okay, so one of the water molecules will gain a proton, the other one will lose. So this is what we are now calling autoionization of water. Water is able to act as a base and act as a base. Okay, so if you look at this equation that we have, this is in liquid, water is liquid. Now the hydronium ion and the hydroxide ions are in aqueous state. So this is now where we are going to begin or start our acid-base equilibrium from. So we know already how to come up with the K expressions. So if you look at this equation, looking at this to be the reactants and that supposed to be the products, how would you put your K expression? Pause the video and try that out. I believe you've done your chemical equilibrium already, you've done your kinetics already. So we said K is only dependent on aqueous and gaseous states. So therefore, In this case, we only have the hydronium ion and the hydroxide ion in the K expression. So this is going to be called Kw because we're talking about water. So the equilibrium constant is referred to as the ion product constant. Okay, so now you need to know that at 25 degrees Celsius, the ion product constant of water is basically equal to 1 by 10 to the power negative 14. This is very easy to remember. The pH ends up at 14, so Kw is 1 by 10 to the power negative 14 at 25 degrees Celsius. That value is going to be very useful as we basically get to proceed. Okay, I also need to mention that the pH ranges from 0 all the way up to 14. Okay, so what makes something to be acidic, neutral, and basic is dependent on the hydroxide hydrogen concentration. So in a case where you've got more of the hydrogen, it is acidic. In a case where you've got more of the hydroxide ions, it is basic. When they are equal, it is neutral. Okay, so I want you to understand that basic is associated with hydroxide ion presence. Acidicness is associated with the hydrogen ion presence. Okay, that's very important for you to basically get to know that. Okay, so we've established to say in a neutral solution the concentration of hydronium or hydrogen ions, in other terms. So hydronium, I believe I've already explained, is the same as hydrogen ion. So in a neutral solution, the hydronium ion are equal to the hydroxide ions. So one example of a neutral solution we can talk about is water. Water is neither acidic nor basic, so we expect that the number of hydroxides and hydronium ions should be equal. Okay, that is very important for us to note that. So since we know that, our K, or our ion product constant Kw for water at 25 degrees Celsius, which is room temperature, is basically dependent on the hydronium ion concentration and the hydroxide ion concentration. Now we've also said that it is 1 by 10 to the power negative 14 at 25 degrees Celsius. Now if we are saying in a neutral solution like water, these are equal, we can use a single letter to represent them, x times x, since they are the same or they are equal, which gives us x squared. So if we try to find the concentration of one of them, we'll basically get that to a point where we find the value of x will be the square root of 1 by 10 to the power negative 14, which is like 1 by 10 to the power negative 7. So that becomes the concentration of what? The concentration of those two in a neutral solution. Okay. Now the other thing that you also need to know is that the addition of pH and POH is equal to 14 at 25 degrees Celsius. Okay. Now that is also equal to the pH plus the POH is also equal to P of Kw. Okay, you understand what I mean by all this. Okay, so the pH, you need to know that the pH is calculated as it is dependent on the hydronium ion concentration or the hydrogen ion concentration. I've already explained those are the same. The POH, as you might guess, will be dependent on the negative log of the hydroxide ion concentration. So this one, whether you just say, you know, acids are associated with hydrogen ion, so it's the same, please. Hydronium and hydrogen, it's the same. Hydronium is just a combination of water with a proton. Okay, so take note of that. So for some of you who are interested in proving all these equations, if you basically get to look at the negative log of this plus the negative log of that, it should be equal to the negative log of the kW, which is 1 times 10 to the power negative 14 at 25 degrees Celsius. Okay. Now there are 3 ways that you can use to measure the pH. I believe you learned these earlier. So the litmus paper can tell whether you have got an acidic or basic solution, or just you can use indicators under titration. You looked at certain indicators, or you can use a pH meter to measure. Okay, just in case I ask you this. So of course, when you know that when litmus paper turns from red to blue, you know that is basic, right? Or alkaline. And then you know that when it turns from blue to red, the pH is acidic. So of course you've got different indicators. You've got methyl orange, phenolphthalein, and all. You can try to research more on basically what basically gets to happen to them at different pH. Okay. Okay, so just before we look at the K calculations, I need to take you back to how to write the K expressions. Okay, let's consider a certain weak acid dissolved in water. So by definition, we've said this indicates partial dissociation. And then we've also said weak bases. Well, that's actually an acid, by the way. Yeah, I've just seen the production of. Yeah. So A is just denoting whatever may be attached. Okay. So an acid in other terms is like hydrogen with something like denoted by A. A full acid would be something like this. Yeah, when I have something like this, that is, for example, an acid. So this entire part is denoted by A. That's what that means. Okay, so this is an acid. So water in this case will act as a base. That's the hydronium ion, and then that is the conjugate base. Okay, I believe I've already explained how to identify the conjugate bases and acids. So this is what brings the issue of equilibrium back. So pause the video and try to write the K expression for this equation. Now, unlike for water, water of course is in liquid state. Acids are in aqueous states. These hydronium ions are all going to be in aqueous states together with the conjugate base. So that being the case, if I was to ask you to write the K expression of an acid, so remember we started with the K expression for water, which is Kw, called the ion product constant. Now for an acid, we call it the Ka, denoting the K of an acid. If you look at our products in this case, we're going to put H3O plus. That is the way you put the K expression. We've already learned that. So it's products over reactants. Reactants, we only have an acid itself. So this is the K expression of that equation. Products over reactants, of course, raise their stoichiometric coefficients, which will, in this case will not be very important because it will be in rare cases where we're going to have such. Okay, so for on practice, I want you to write an equation that will show the dissociation of this acid in water, and then I also want you to write the K expression for that acid, Ka expression for that acid. Okay, so hoping you've paused the video and you've already answered. So we're just going to say plus water, and then it is a weak acid, so we expect it to production of hydronium ion after a loss of a proton, and then after it has lost a proton, it will become COOH, and then it will become negative. Or people prefer to actually lose the proton in front there so that it becomes like that, but it's all the same anyway. So say plus HCOO negative, meaning that that hydrogen has been lost. Okay, so you know water is in liquid, everything else is in aqueous state. So the K expression will be those ones divided by the acid itself. Okay, so just before we get to go into a detailed video where I've looked at several questions on this topic, I want us to understand how we get to calculate the Ka or the Kb if you're talking about the base. Okay, so let's take this very example. The pH of is 0.1 molar concentration solution of formic acid So the formic acid itself is HCOOH at 25 degrees Celsius is 2.38. Calculate or find Ka of the acid at that temperature. How are we supposed to approach the question? How do we handle it easily? So this is now where the ice table comes in. So this is where the equilibrium part of the topic comes into picture. So we know the ice table requires us first of all to write the equation. So let's try to write the equation. So we have an acid, HCOOH. Now this acid is of course going to be dissolved in water. So even if you don't show the water, it's not important. Okay, well, for argument's sake, we'll say it's not dissolved in water in this case. Doesn't matter anyway. But anyway, so let's assume it's okay. I'll go by that. So give us, so it will lose a proton. So a proton will be there now. Now in a case if we add water, the only difference is we are going to have water here, and then the hydrogen ion will be the hydronium ion there. So even if we show the water does not appear in the K expression because it is in liquid state. So even like this equation is still sufficient for us to come up with a K expression. Okay. So the ice table shows the change. That's what is called the ice, and also the equilibrium concentration. So now K expression, one thing you know about the K expression is that it's dependent on the equilibrium concentrations. Alright? It is dependent on the equilibrium concentrations. Now if you look at the question itself, at start the concentration of the acid was given to be 0.1. Zeros are not important, 0.1. So obviously at start we didn't have anything of the other side, those are products. So at starting we only had an acid, so we had 0 molar concentrations of the products. Okay, so now the question is, how are we going to find the equilibrium concentrations? How are we going to find the equilibrium concentrations? Now the other thing is the pH has also been given. So take note of that. pH has been given to be 2.38. So pH has been given to be 2.38. So that's part of the piece of information we have. Now remember I told you, say the pH can be found to be the negative log of the hydrogen ion concentration. Okay, so we can equate that. So the pH has been found to be 2.38. So the pH of formic acid is 2.38. Calculate Ka for formic acid at this temperature. So let's try to find the hydrogen ion concentration. So you can divide both sides by negative. So the negative will go there, and then this has got +10. So the hydrogen ion concentration becomes 10 to the power negative 2.38. So after calculating that, the hydrogen ion concentration at equilibrium is going to be equal to 4.16 times 10 to the power negative 3. Now for the change, we have to look at what we call the stoichiometric coefficients. For the reactant, it reduces as the reaction proceeds. By the way, I'm not supposed to put a full arrow there. This is equilibrium, so we also have a backward reaction. And then for the products, we will add plus because there is an increase in concentration. Okay, so the equilibrium will be like so this one will be 0.1 minus x, the others will just be plus x. Now the fact that we've used the pH to find the hydrogen ion concentration, so you can come up with a relationship there where you can say your x, your 0 plus x is equal to 4.16 times 10 to the power negative 3, which just tells us that x is just equal to that. So therefore, even for the x of the conjugate base will also be 4.16 times 10 to the power negative 3. So even where we have x there, again we'll have to substitute first to get the equilibrium concentration. So at this point we are now ready to find the Ka. I need to mention that if we are given the POH, that works when you're dealing with bases. You're also supposed to say the negative log of the hydroxide ion concentration. You equate it to the value given. Divide by negative both sides. Use the laws of logs. Take the term the other side, and you should be able to find the value of the hydroxide ion concentration as well. And in this case, our Ka is dependent on the products. The products we have 4.16 times 10 to the power negative 3 for the first one, the other one as well, and then divided by our only single reactant in aqua state, 0.1 minus 4.16 times 10 to the power negative 3. From there we should be able to find the value of Ka. So on my calculator I'm trying to perform everything. 0.1 minus that divided into that. Okay, so the answer I'm actually getting here is value of Ka is equal to 1.81 times 10 to the power negative 4. So Ka has got no units. Okay, so we'll use this theory example to basically get to explain what percent ionization is. So percent ionization is just as it tells, is looking at how much has been ionized over what you had initially, or original in other terms. So what has been ionized out of the initial, the total, multiplied by 100. So in this case, since we had an acid there at start, the initial concentration was given in the question. Now the ionized amount of it, how much of it was ionized. In other terms, you look at or what amount of it was like converted to the proton ions. So if you check there, the hydrogen ions were that on the other side. So about 4.16 of it are basically ionized. So when you talk about the percentage ionization of an acid, you focus on the protons. Okay. So in this case, you get the equilibrium value. Okay, you get the equilibrium value of the acid, or rather the proton that's dissociated or ionized, and then you divide by the initial amount of the acid that you had, multiplied by 100. So in this case, it will be 4.16 times 10 to the power negative 3 over 0.1 times 100, which will give us 4.2%. Okay. So in a case, of course, we are talking about the base, it will be the same. You look at how much of the hydroxide has been produced, and then divided by the base you had times 100. That's how you determine the percent ionization. Now, in the next video, you will learn a lot. So from question 6, you will learn how to calculate the pH, how to calculate the POH, you will learn how to find the Ka, how to find the Kb, you will learn how to find the Kw. You also look at acid-base titration, you look at how to identify the conjugates and the bases, you look at every aspect of acid-base equilibrium. Any form of questions you might expect in the exams are covered in the next video. Video is 1 hour 6 minutes. So after that video, we'll now proceed and talk about polyprotic acids. It's very important that we get to understand what an acid is and what a base is. So we have what we call an Arhenius acid. So Arrhenius came up with a definition of an acid and a base. Okay, so we have Arrhenius acid and base. So an Arrhenius acid is basically defined to be anything that increases the concentration of the hydrogen ion. So increasing the hydrogen ion concentration, that is an Arrhenius acid. Then an Arrhenius base is defined to be anything that increases the hydroxide concentration. Okay, so that's what we have. So adding an equation to show that, how basically can we show it? So what we can say is, for example, if you have HCl as an acid, according to Arrhenius, this is going to dissociate into an hydrogen ion and a chloride ion. So the fact that the acid is basically losing that hydrogen concentration, it is increasing the concentration of that in the solution. So that is the definition of an acid, an Arrhenius acid. Okay. Then when you talk about Brotsted, so there's also what we call Brotsted, and this is going to be the most useful one. Brotsted, definition of an acid and a base. So this one says an acid is basically a proton donor, then a base is a proton acceptor. Okay, so in this case, talking about a proton, talking about an hydrogen ion. So you find that anything that we consider to be an acid is basically supposed to lose a proton. So for example, in this case, when you have let's say CH3 COOH as an acid, so you basically, it dissociating in water is going to be the fact that it is going to lose that proton, so it will become the acetate ion. Okay, so the loss of the hydrogen there is what is making it to qualify to be a Brotsted acid, because it has donated the proton. Then water in that case is going to gain and it will become the hydronium ion. Okay, that is very, very important to understand. Another thing that is very key to understand is that acidicness is determined by the presence of hydrogen ions. Then something to be basic is supposed to contain the hydroxide ion. So the presence of hydroxide ions indicates that something is basic. Very, very important. Okay. Another thing that is important is for you to understand some of these equations. So the pH is basically dependent, like I've mentioned, is dependent on the concentration of the hydrogen ion or the hydronium ion.
Okay, so in some textbooks you can meet this, which is the hydronium ion. So it's basically one and the same thing. Then the POH on the other hand is basically dependent on the concentration of what? The hydroxide ion concentration. Okay, so there's something that we have to understand. pH plus POH is basically equivalent to 14. We also have to understand that the Ka multiplied by Kb, where Ka is the constant of an acid and the base. So these are equal to what we call Kw, which is the ion product constant. And basically, when we talk about the standard conditions, you find that the products of Ka and Kb are basically going to be equal to 1 by 10 to the power negative 14. So that is also very, very important for you to understand. So these are some of the basics. Others will get to meet them as we look at the practice questions. Question 1. Write the dissociation reaction and the corresponding Ka equilibrium expression for each of the following acids in water. Okay, so basically you have to look at the given acids here. It's very, very important to understand that the difference between strong acids and strong and weak acids. So when you talk about a strong acid, it's basically an acid that dissociates completely into its components. So for example, if you talk about HCl, this one is supposed to dissociate completely into its ions, like that. But talking about a weak acid, like for example, if you talk about an example of acetic acid, you'll find that it will not dissociate completely. What will happen is that it's only going to lose that hydrogen. So it will form what we call the acetate ion, and also what? And also the hydrogen ion, which is going to combine with the water molecule to give us what we call the hydronium ion. So now if you look at the question, what kind of bases, what kind of acids have we been given? Because I want us to find the Ka expression for that. So basically, if you look at HCN there, that these are weak acids. Okay, so what we are going to have is we have to write what we call a dissociation reaction. Dissociation reaction involves you dissolving this kind of an acid in water. So for the first part, what we have is HCN being dissolved in water. So the dissociation reaction that we basically have is, so what did we say? According to Brotsted, we were told that an acid is something that is supposed to donate a proton. So it was basically going to lose what? Basically going to lose the hydrogen there. So what we have is Cn. So the moment it loses a proton, it will have a negative charge. Then on the other hand, the water molecule is going to gain, because it's a base in this case. So we have HO3O. So it will be a positive. So we call that an hydronium ion. Okay. So this is our dissociation reaction. So remember all these, that is in aqueous, the water is in liquid, everything else is in aqueous. So from chemical equilibrium, we understand that the constant K, which in this case is Ka, is only dependent on the things that are in aqueous and gaseous state. So the water that is in liquid state is not going to be part of the expression. So basically what we're going to have is what are the products there? So we have Cn minus, then our hydronium ion as well. So this is supposed to be divided by the acids. So of course we made a point to say you're supposed to raise them to stoichiometric powers. So all these is just 1, 1, so it's just 1, 1, and nothing will change about it. So that is our dissociation reaction as well as our Ka expression for the first part. The second part, what would be the dissociation reaction? So what have we been given? We have that. So we have HO, C6, H5. So dissociating in water. So of course take note of the states there. That is aqueous, this is liquid. Okay. So basically, it's also very important to make sure that you show this, because this is in equilibrium. It's something that is reversible. Okay. So we're supposed to lose a proton there. So we have OC 6H5. So it will be a minus. Then this part is going to gain. So what is in aqueous? Aqueous. So our K expression in this case is basically going to be, look at our products, okay, then divided by what? Divided by our reactants, which is just only 1 because something in liquid state doesn't appear in the K expression. Okay, so that's how you answer the second part of the question. Try out the C. So basically we have C6H5NH3 plus. Okay, so in water. So what do we expect there? So we are expecting this part, since it's an acid, to lose a proton. So look at the initial charge here. So C6H5NH2. So it's supposed to be what? There will be no charge there because it's moving from a positive 1 to a 0 charge. If it was a 0 charge initially, it would have become a negative. But in this case, it will remain as a positive there. So the delta will gain and it will become the hydronium ion, giving us a positive charge there. So basically our K expression, so it's going to be dependent on the product of that, multiplied by the hydronium ion concentration divided by the acid itself. So only the water doesn't appear because it's basically in liquid states. Question 2. Question 2, we ask to identify the acids and their conjugate bases. So basically we've understood that an acid is basically something that donates a proton. So donates a proton according to Brotsted law. Okay. Then a conjugate base. So we are talking about a base basically to be something that is supposed to do what? A base is a proton acceptor. Okay. So now if you talk about the conjugate base, what I want you to understand is a conjugate base is basically the opposite of what? An acid. Okay. But on the product side. So if you say, you look at the first reaction there, which one is an acid? So if you try to assess, you find that this part is the one that has lost a proton and it has become that. So this reaction, remember this reaction is reversible, meaning that we are able to go back to the other side. So now if you look at this, consider them to be your reactants. So the acid now becomes the conjugate base because on the other side it's able to gain a proton and go back to the acid form. Okay. So the acid on the reactant side becomes the conjugate base on the other side. It's a conjugate base because it's able to gain a proton again and go back to its original form. Okay. So as you might guess, a base also has got what we call a conjugate acid because when it gains a proton, on the other side it has got the ability of, so this one basically on the other side it was a base, now here it's a conjugate acid because it has got the ability of losing a proton, donating it to the other part. So that's why it's also called a conjugate acid on the other side. So in the first reaction, that one is our acid and that is its conjugate base. In the second reaction, which one has lost a proton? So it's basically NH4 and that is its conjugate base. In the third reaction, which one has basically lost? It's this one. That's its conjugate base. Then for the last one, just like that. So we've identified the acids and their conjugate bases in this question. Third question, identify the bases and their conjugate acids. So for the bases, what do you do? You look at something that has gained. So for the first reaction, these are identical. So you can get any of them, consider any of them to be your base. Okay, so this is what we call autoionization of water. Water is able to act as a base as well as an acid with itself to form a hydronium ion and an hydroxide ion. Okay, so at that point what we are saying is that is our base. Then the conjugate acid is something that has got the ability of losing a proton on the other side. So it's basically the hydronium ion is a conjugate acid from that point because it's able to lose and go back to its acidic form. For B, is it NH3 or the water which has lost? So basically, it's H2O. It is basically the one that has lost and it has become the hydroxide ion. So now we are interested in identifying the base. So which one is the base? The base is something that has accepted. So it's basically the NH3 which has accepted and it has become that. So the NH4 is a conjugate acid because it has got the ability of donating a proton so that it's able to reverse and go back to the ammonia form. Question 4. The following chemical reactions are important for the industrial processes. Identify the acid-base pairs. So acid-base pairs. So basically from Brotsted we are told that an acid is something that is supposed to donate a proton. Okay, so basically that has donated. Okay, so what are we saying in this question? Identify the conjugates acid base pairs. Okay, so we're asking for the conjugate acid and the base pairs. So which one is our base? Our base is something that has done what? So our base is something that is supposed to gain. So that is our base and that is their conjugate acid. In the second part of the question, which one is our conjugate acid or which one is our base? So our base is something that is gaining a proton. So that is basically our base. It has gained a proton. So on the other side, this is what we are calling the conjugate acid because it has got the ability of donating a proton to go back to the other side. Then in the last part of the question, which one is the base? So that is our base and that is the conjugate acid. So we've identified the conjugate acid with the base pairs. Question 5 is a bit different. Calculate the pH and the POH for the following solutions. So if you look at what is been given in this case, if you look at the first part of the question, that is a strong base, a strong acid, a strong base. So basically these get to dissociate completely, meaning that the sodium hydroxide is supposed to be broken down into its ions completely. Okay, so how do you get to calculate the pH? So you get to calculate the pH by writing first of all the dissociation reaction. So you say, okay, sodium hydroxide, basically, if it dissociates, it's supposed to be broken down into its ions. So we have sodium ions and what? And the hydroxide ions. So these are the ions. So these are the ions that make up sodium hydroxide. Okay. So that is in aqua state. That is also in aqua state, in aqua state. So now, what is the concentration of the sodium hydroxide? It's basically 0.02 molar concentration. What is the concentration of sodium and hydroxide ions? So if you look at this, they are basically in the ratio of 1 to 1. Okay, in the ratio of 1 to 1. So if this is at 0.02, if it dissociates completely, all of these are going to be in the same, are going to have the same concentrations. Okay. So the question is asking us to find the pH and the POH. So basically from the start of this video we said that the pH is basically dependent on the negative log of the concentration of the hydronium ion or the positive ion. Then for the POH we basically say it is dependent on the negative log of the hydroxide concentration. So in this case what we have hydroxide concentration because we're talking about the base. So it's going to be the negative log of the concentration, which is 0.02. So get your calculator, negative log of 0.002. So what we have as a POH is basically 2.7. So that is our POH. Okay, we also made another point to say that considering standard conditions, the summation of pH and POH is basically equivalent. POH basically is equal to a 14. So if we found our pH for our POH for the first part of the question, we're able to find the pH as well. So our pH is basically going to be 14 minus our POH, which is 2.7. So 14 minus 2.7, we have 11.3 as our pH. So basically, you know that a pH below 7 is acidic, above 7 it's a base. So basically, this is able to tell us that what we're talking about is a base there. Okay. The second part of the question, we have the acid instead. So you can write the dissociation reaction. So HCl is a strong acid, which is also going to dissociate completely. So meaning that the concentrations, the initial concentration will be the same if you look at the mole ratios, well. So it will be basically the same. So what are we able to find? So we have the hydrogen ion. So we're able to find the pH. So the pH is going to be the negative log of. So basically, if we add water there, it's going to be the hydronium ion. This part combined with water is going to be hydronium ion. So that's why we are using its concentration. So what is the negative log of 0.134? So what we have is our pH in this case is basically 0.87. So this is a clear indication that since the pH is below 7, it's acidic. And basically what we have is an acid. It makes sense. So our POH on the other hand is basically going to be, remember we said pH plus POH is equal to 14. So therefore our POH is going to be 14 minus the pH, which is 0.87. So 14 minus what? What basically we have is a 13.1. So what we found there is what? Is our POH for that reaction. Oh, yeah, that concentration or solution. Then part C. What we have is something that is a base, but it's a strong base. Okay. So barium hydroxide 2. So for the dissociation reaction, it's going to be a bit different from what we've been talking about. Okay, so this is also complete dissociation. So we have barium 2 plus in addition of 2 hydroxide ions. So this is how different it is. What is the initial concentration? It's 0.03. So there it will be the same. So now if you look at this, barium hydroxide is in the ratio of 1 to 2 to the hydroxide ion. So you're saying 1 to 2. So if you have 0.03 there, meaning that it's supposed to be doubled at the concentration on the other part. So it's basically going to be 0.03 by 2, which is going to be a 0.06 molar concentration. Because we are saying for every 1 mole of barium hydroxide, we have 2 moles of hydroxide ions being produced. So the concentration is going to be double the initial concentration. So, and this is only a case where it's a bit different. So what we have is an hydroxide. So we're able to find the POH. So the POH is going to be the negative log of that concentration, which is 0.06. Okay. So negative log of 0.06. So what I have is a 1.22. To find our pH, it's 14 minus the POH. So I'm finding a 12.8. So we found the pH and the POH of these solutions from this question. Question 6. Calculate the following. So for the first part, we are saying the hydronium ion in 0.20 molar solution of acetic acid. K for that reaction has been given. So we're trying to find the concentration of the hydronium ion. So the first thing that we can do is write the dissociation reaction. So what we have is acetic acid. Okay. So after dissociation, so I can even omit the water there because it's in liquid state and it doesn't appear. It's not part of the K expression. So we just have that. So we use this to show that it's partially dissociation because it's a weak acid. Then what is it dissociating into? So it's the acetate ion. So it has lost a proton. then what we have is an hydrogen ion. So if we had shown water there, this part would have been a hydronium ion. So it's basically the same, no difference. Okay. So what is the initial concentration? What initial concentration have we been given? So we've been given 0.20 molar concentration. So what we get to use to help us is what we call the ice table. So the ice table is very applicable. Okay. So if you've not understood what an ice table is, I would advise you watch our video on chemical equilibrium. So an ice table will give you the initial concentration, the change, and also what? The equilibrium concentration. So initially, when starting this reaction, basically we only add the acid. These others were not present according to the information given in the question. So meaning that there was no concentration of that and no concentration of that. So the change is basically dependent on the coefficients. So for the reactants, we get to use the negative to show that it's actually being depleted or being used up. So what is the coefficient there? It's a 1. So we are going to say minus x. And for this part, we're going to say plus because we expect the products to increase in concentration as the reaction progresses. So for the equilibrium concentration of the acid, what we have is 0.2 minus x. For this part, we just have plus x plus x. Okay, so we've been given the value of Ka, but we know how to find the Ka value. It's basically dependent on what? So I can erase this. Okay, so we know that our Ka value is basically going to be dependent on the products, which is the acetate ion and what? And the hydronium or the hydrogen ion divided by the acetic acid concentration. So we're able to plug in the values that we have. So what we use is the concentrations at equilibrium. So we have our concentrations at equilibrium. We have x 0.2 minus x. So we're able to plug in. So for the acetate ion, what we have x. What we have for the hydrogen ion is also x. Then what we have for the acid, so the acid we have 0.2 minus x. What do we have for our Ka value? Our Ka value in the question has been given to be 1.8 by 10 to the power negative 5. So for the people who've done chemical equilibrium, we understand that whenever you're trying to find the value of x, whenever the value of K is less or low, basically below 0.1, so it's basically what you can do is just to cancel out every part that is having either an addition or a subtraction of x to avoid having a complicated quadratic function. So basically we'll cancel the minus x there, so that it's basically just gets to multiply, because at the end of the day, basically if you try it out, you are going to find the same solution. To save on time, we just cancel it out. So what we have is x multiplied by x is basically x squared. So we now have 0.2 being multiplied with 1.8 by 10 to the power negative 5. So all we've done is multiply that part with this part down there. Okay, so grab your calculator, 0.2 multiplied by 1.8 by 10 to the power negative 5. So 1.8 by 10 to the power negative 5 multiplied by 0.2. So what I'm finding is x squared is basically equal to 3.6 times 10 to the power negative 6. So finding the square root of that, we basically have a 1.9. So we have 1.9 as our value of x. In this case, 1.9 by 10 to the power negative 3. Sorry. So that is our value of x. So remember, what did we have as at equilibrium? So for the acetic acid, we had 0.2 minus x. Then for the acetate ion, we had x and x there. So meaning that we've already found the concentrations of the acetate ion and what? And the hydronium ion. So what we've found there is basically our value of the hydronium ion concentration. And that's how you go about it. Okay. Question B. We are also asked to find the hydronium ion concentration in 0.20 molar concentration of HCN. So basically we even know what is going on now, so you can even save on time. Okay, so let's rate the dissociation reaction. So what we have is HCN. This time around, let's show the water molecule so that you see where the hydronium ion is coming from. So what we have as a products is that being an acid supposed to donate a proton, so it will be Cn minus. Then the other part is going to be the hydronium ion, meaning that the water molecule has gained a proton from the acid. Okay, so at this point what we can say is, without even showing the ice table, you can say, okay, my Ka value is going to be equal to, so the liquid water doesn't appear in the equilibrium concentration, only the aqueous solutions. Okay, so for our Cn, it's basically going to be, because these are in the coefficients of 1, 1, so it's basically going to be x multiplied by x as our equilibrium concentration. Then for this part, it's going to reduce in concentration. So what is the initial concentration? It's 0.2. So it's going to be 0.2 minus x. So that is a shortcut. So it is x squared over 0.2. So we say this part is to be cancelled out. Okay. So what is the value of Ka? The value of K has been given to be 4.9 times 10 to the power negative 10. So if we have that, we're able to find. Let me show it side. So our value of K is 4.9 by 10 to the power negative 10. So making x squared to be the subject, so we have 4.9 times 10 to the power negative 10 being multiplied with 0.2. Okay, so this part is being multiplied with that part. What I'm getting is a 9.8 by 10 to the power negative 11. So from there, now finding the actual value of x, the root of that. So we basically have 9.9 times 10 to the power negative 6 molar concentration. So what you found is the concentration of that ion and also the hydronium ion. So finding the equilibrium concentration for this would be subtracting the initial with what we found. But in this case, we are interested only in the concentration of the hydronium ion. Question C. Find the hydroxide ion concentration in 0.1 molar concentration of NH3. So this time around we have Kb, meaning that what they're asking for is basically the constant for a base. So our base is basically NH3. So for the dissociation reaction, what we expect that this time around, this is basically going to gain a proton and the water is going to act as the acid. Okay, so we're basically going to have NH4 because it's a proton. Then we are going to have an hydroxide ion that being formed. Okay, so the same can apply. Our Kb is going to be equal to, what will be the equilibrium concentration there? So we'll say x times x. Then for the base initially it was 0.1, so it's going to reduce by x. So this is going to be x squared over 0.1. So we said whenever the K value is below at least 0.1, we can cancel this part to avoid having a quadratic function. Okay, so we can plug in the value of Kb on the left. Our value of Kb is given to be 1.8 by 10 to the power negative 5. So finding our value of x squared, 0.1 basically is being multiplied with 1.8 by 10 to the power negative 5. So what I'm getting after multiplying is basically 1.8 by 10 to the power negative 6. So finding the root of that, what would be our value of x in this case? So the value of x that we're going to find is basically going to be the concentration of the hydroxide ion. So the square root of 1.8 by 10 to the power negative 6. So it's basically 1.34 by 10 to the power negative 3 molar concentration. So we've answered part C. Part D. The pH of a solution of 25 milliliters of 0.20 molar concentration of sodium hydroxide is added to the HCl. So this is a question that makes you or requires you to have a great understanding of acid and base titrations. So what you have is you have your sodium hydroxide being reacted with the HCl. So we said the acidicness of a solution is basically determined by the presence of the hydrogen or the hydronium ions. Then the concentration, or basically the alkalinity, is determined by the presence of the hydroxide ions. So for us to be able to find the pH of this solution, it's very important that we get to find which of the two is going to be in excess. Okay, so this is a neutralization reaction. So basically these are reacting to give us water and sodium chloride. So these are neutral. So I want to remove everything that is neutral and remain with the excess, and therefore the excess is going to be the determining one. Let's do that. Okay, so what have we been given? We've been given for sodium hydroxide, the volume is 25 milliliters. The concentration is basically 0.2. So 0.2 molar concentration. For HCl, we have 40 milliliters. The concentration is 0.15. Okay, so let's try to find. So these guys react in the ratio of 1 to 1. So that is even easier. So meaning that an equivalent number of moles are going to be used up. So I believe we understand that the concentration is basically given as the number of moles over a volume. So we already have the concentration in this case. We also have a volume, so we can find the number of moles. So the number of moles for the first part is going to be a product of the concentration 0.2 multiplied by the 25. So the 25 milliliters there is basically multiplied by 10 to the power negative 3. So that is in liters. So that we find the number of moles. Then for the other part of the HCl, the number of moles of HCl are going to be 0.15 multiplied by 40 by 10 to the power negative 3. So let's find the number of moles of the sodium hydroxide to start with. So grab your calculator, 25 multiplied by 10 to the power negative 3 multiplied by 0.2. So what we have there is 5 by 10 to the power negative 3 moles. Then for the other parts, we have 0.15 being multiplied by 40 by 10 to the power negative 3. So what we have is 6 by 10 to the power negative 3 moles. So we now have the value of moles that were there initially. We can even remove that information there. So for a number of moles, for sodium hydroxide we had 5 by 10 to the power negative 3 moles. For the acid we had 6 by 10 to the power negative 3 moles. So we have the number of moles. So now, how do you get to determine the limiting reagent there? Which one is limiting, or which one is going to finish faster? So these are reacting in the ratio of 1 to 1, meaning that an equivalent number of moles of sodium hydroxide are going to react with an equivalent number of moles of sodium hydroxide. So the smaller one is basically the limiting reagent. So 5, we'll subtract 5 by 10 to that are going to be used up, will remain with a 0. Then 5 of HCl are required to react with the sodium hydroxide. So we'll remain with 1 by 10 to the power negative 3 moles. So meaning that the sodium hydroxide is going to be used up to form water and sodium hydroxide, which are neutral. So what you're going to remain with is only the number of moles of HCl. Okay. So basically we have the moles of HCl in excess, which is basically the important information that we needed in this case. So these are the ones now that are going to determine. So this tells us to say that what we are going to have is an acidic state, because the HCl or the acid was more in concentration as compared to the base. So this is HCl in excess. The other part was neutralized. So we have the number of moles. We need to find the concentration, because we basically know that the pH is basically dependent on the negative log of the concentration of the hydrogen ion. Of course, we know the HCl is basically gets to dissociate completely. So HCl will give us the hydrogen plus a chloride ion. So its concentration there as an acid is basically equal to the concentration of the proton, which is going to give us the value of pH. So we know that our concentration is given as the number of moles divided by the volume. So for our number of moles, we have 1 by 10 to the power negative 3. Then for our volume, what do we have? So now we had combined 25 moles with 40 moles. So the concentration that we had is 25 plus 40, which is basically 65 moles. So 65 milliliters, we need to convert that to liters. So it's we multiply by 10 to the power negative 3 as well. So this is in liters, that is in moles. So what we're going to have is a molar concentration. So basically 1 divided by 65. So what basically do we have in scientific notation? So what we have as our concentration is basically 1.25 by 10 to the power negative 2 molar concentration of the HCl. That is how much was in excess. So therefore, our pH is going to be dependent on that. So it's going to be the negative log of that. So negative log of 1.5 by 10 to the power negative 2 molar concentration. So you can grab your calculator there, negative log of that. So what basically I'm getting as my value is basically a pH of 1.8. So that is our pH, which tells us that it's acidic. The solution was acidic because we had more of the acid than the base. Part E of question 6 says the base dissociation constant for the fluoride ion. Given that the value of K is basically equal to that. Okay, so what we have is a base dissociating. Okay, so the assumption that we have is we are saying that this base was dissociating at what? At standard room temperature, where we are saying at 25 degrees Celsius. The product of our Ka and our Kb. So this is the acid dissociation constant, that is our base dissociation constant, is going to give us what we call Kw, which is the acid base, of course, product there. Okay, so now we said at room temperature is basically equivalent to 1 by 10 to the power negative 14. That's a point that we had made there. Okay, so we have been given the value of Ka. How are we going to find the value of Kb? So the same principle is going to work there. You plug in the value of Ka. So our Kb is basically going to be 1 by 10 to the power negative 14. So basically a correction there. Ka multiplied by Kb is what we call the ion product constant. Okay. So let's try to figure out that. So you divide by a value of Kb there. So what is our value of... Sorry, yeah, we divide by the value of Ka, which we've been given. So we have 3.5 by 10 to the power negative 4. So after dividing there, what value are you going to get? So what I'm getting as my value is basically my Kb is equal to 2.9 times 10 to the power negative 11. So we found the value of Kb.
Are you enjoying this video lesson? So you can actually access the entire topic you are watching or the entire practice questions of a video that you may be watching right now. So if you go to our website is transcendentinstitute.net. Okay, so there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. So alternatively, you can access the videos using our learning portal. The link is learn.transcendentinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets, which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course, this applies to all these other topics that are available. Trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So if you open chemistry, these are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the tutorial sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally, biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel.
The last part of question 6. Find the pH of 0.1 molar solution of sodium cyanide, given that the Ka is what? So if you don't know if what they've given you is an acid or a base, just look at the constant that they've given you. So if they say Ka, it means that you're talking about an acid. So HCN being an acid, we expect it to donate according to Brotsted Lowry definition of an acid. So it's going to donate the hydrogen ion, and what is it going to do? It's going to lose it to become a negative. So that is cyanide there. Okay, so we're trying to find the pH. What was the concentration of the sodium cyanide? So the concentration initially was what? Of course, I'm not showing the sodium cyanide. It's basically, it's just a matter of adding a sodium there, but it has got no law in the calculations. Okay, so what we have is 0.1 molar concentration of the sodium cyanide. Then what we're trying to find now is the value of, or we're trying to find the pH here. So this is the initial concentration that we have there. So what is our change? Our change is a minus x. Then for this one, initially we add nothing. So then basically what we have is the change here is a minus x. Or basically the products gets to increase, so it will be products. So what we have there is our equilibrium concentration is 0.1 minus x. We have a positive x and a positive x. So we know that our value of K is basically dependent on the equilibrium concentrations. So our K is going to be x squared over 0.1 minus x. Our value of K has been given in the question to be 4.9 by 10 to the power negative 10. Okay, so at that point what do we have? So our x squared, so we said whenever the value of K is low, no need of you working out a quadratic function, so you cancel out that part. So your x squared is equal to 0.1 multiplied by 4.9 by 10 to the power negative 10. Okay, so you can grab your calculator there and plug in the values there that we have. So after multiplying and finding the square root, the value of x that I'm finding is basically 7 by 10 to the power negative 6. Okay, so we said that is basically going to be the concentration of what? The hydrogen ion and also the cyanide there, because these guys are in the ratio of 1 to 1. And what we said is that equilibrium, only that is going to be different from the solution, because it's basically going to be the initial 0.1 minus x. Then the rest we said they were just x and x. So that is our concentration of the hydronium ion, on which we know that that is where the pH is. That is what the pH is dependent on. So basically our pH in this case is going to be the negative log of that concentration. So 7 by 10 to the power negative 6. So therefore our pH in this case is going to be 5.2. And we've answered it. Okay. We are now on question 7. At 40 degrees Celsius, the values of Kw, so that is the acid base, or we say the ion product constant, is basically 2.92 by 10 to the power 14. So remember at 25 we said it's 1 by 10 to the power negative 14. But for the sake of this temperature, which is not a standard temperature, we've been given the value of the ion product constant. So what you need to understand is basically from the start of this video we made a point to say Ka multiplied by Kb is basically equal to that. Then we also made a point to say the hydrogen concentration or the hydronium concentration is basically multiplied with hydroxide ion to give us a Kw as well. So now what you need to understand that when you're talking about pure water, the concentration of the hydrogen ions are equivalent to the concentration of the hydroxide ions, because we said the acidity is determined by the protons, then the hydroxide ions determines how alkaline something is. So basically if we expect it to be pure, and we understand that water is basically neutral, meaning that there are no excess ions there, they are basically equal. The protons are basically equivalent to the hydroxide ions. Okay, so in this case, applying the same concepts, we know that the product of the hydrogen ions multiplied by the hydroxide ions are basically going to be equal to the Kw, which in this case has been given to be 2.92 by 10 to the power negative 14. So what are we interested in? We're trying to find the concentration of the two, and we know that their concentrations are the same in pure water. So we can put x to represent each of them. So it's going to be x by x, which is basically going to be x squared, is equal to 2.92 by 10 to the power negative 14. So from there we're able to find the value of x. So therefore the value of x is going to be the root of that. So what you're saying is that the hydrogen concentration, which is equal to the hydroxide concentration in this case, is basically going to be the root of 2.92 by 10 to the power negative 14, which is basically 1.7 by 10 to the power negative 7. So we found the concentration of the hydrogen ions as well as the hydroxide ions. So now the second part of the question says, what is the pH? So we made a point to say that the pH is basically dependent on the concentration of what? The hydrogen ion. So it's going to be the negative log of 1.7 by 10 to the power negative 7. So therefore our pH is going to be negative log 1.7 by 10 to the power negative 7. So the value that I'm getting is basically 6.8, which is closer to 7. So that is our pH there. Okay, which makes sense because we're talking about pure water, which should be closer to 7. C says if hydroxide ion concentration in solution is what is the pH at 40 degrees Celsius? So what have they given us there? They've given us the hydroxide ion concentration. Okay, so let's try to work out that. So we said the pH plus the POH is basically equivalent to 14. Then we said if you've given you the hydroxide ion concentration, you're able to find the POH. So we said the POH is going to be the negative log of what? The negative log of the hydroxide concentration, which in this case has been given to be 0.1, is equal to 14. So finding the pH value is going to be 14. So negative log of 0.1 is basically 1. So if it goes the other side, you subtract 1, it's basically going to be the pH of 13, which basically shows that when you have the hydroxide ion concentration, the solution is basically basic. Question 8. A student prepared 0.1 molar acetic acid solution and experimentally measured the pH to be that. Calculate the Ka for the acetic acid and determine its percent dissociation. So the value of Ka. So we made a point to say that it's very important to come up with what we call the dissociation reaction. So in this case we have acetic acid, which we know is CH3 COOH. So this is basically dissociating to give us the acetate ion, which is basically losing just the proton there, giving us a proton. Okay, So what is the initial concentration? The initial concentration that we have is basically has been given to be 0.1 molar concentration. For the acetate ion, initially we didn't have anything, so we can just put 0 there. Then the change is basically dependent on the constant there, so minus x. Then what can we say there? We can say that is plus x. That is also plus x. This is 0.1 minus x, that is x and x. Okay, so we have the value of pH here. So what did we say? What we said is pH is basically equivalent to the negative log of the concentration of what? The proton there. Okay, so what we can do is we can try to find the concentration of the hydrogen ion, which will give us a value of what? Which will give us a value of x. Okay, let's try to do that. So we have our pH here. Our pH has been given in the question to be 2.88. Okay, so we have a negative log of that. So this is in base 10. How are we going to do it? So we can divide by a negative on both sides. This one will become positive and that one will be a negative. So therefore the hydrogen concentration in this case is going to be, this 10 can go the other side from the laws of logarithms, so it's going to be 10 to the power negative 2.88. So 10 raised to the power negative 2.88 okay, so what I'm getting as the concentration of the protons is basically 1.3 times 10 to the power negative, let me write that better, 1.3 by 10 to the power negative 3 molar concentration. That is at equilibrium of the hydrogen ion, which is equal to x there. Okay, so now the question was asking us to find the value of Ka. So we basically understand that the value of K is dependent on the equilibrium concentrations. So we said for a product we just have x and x, so it's x squared. Then for our reactant we add the initial concentration 0.1 minus x. So okay, what are we trying to find? We're trying to find the value of what? Ka. So we have our x has been found to be 1.3 by 10 to the power negative 3, so it is squared over 0.1 minus 1.3 by 10 to the power negative 3. So at that point we can now plug in and see the value that we're going to get for our Ka. So our Ka is going to be equal to, so that squared divided by 0.1 minus 1.3 by 10. Okay, so what I'm getting is basically my K to be 1.76 times 10 to the power negative 5. So we have found our value of Ka. The other part of the question is asking us to find the percent dissociation, how much of it are dissociated. Okay, so remember we said for weak acids they don't dissociate completely. So what we had is CH3COH dissociating. Then what is it giving us? So basically we said initially, I think I can just focus on this part. So the initial concentration was basically given to be 0.1. So the initial was 0.10 molar concentration. Now the equilibrium concentration was 0.1 minus the answer there. Okay, so 0.1 minus 1.3 by 10 to the power negative 3. So let's try to do a calculation. As 0.1 minus 1.3 by 10 to the power negative 3. So what we have is 9.87 by 10 to the power negative 2. So that is what we have as our equilibrium concentration there. So now the percent dissociation is how much had been lost. So initially what did we have? Okay, so we'll say what we had initially was 0.0 molar concentration. Now how much was used up? So how much was used up with this part? That's how much was used up. So that is how much I dissociated by 100. Okay. So the 1.3 by 10 to the power negative 3 divided by 0.1. Okay. So multiply by 100. Multiply by 100. I'll do that again. So we have 1.3 by 10 to the power negative 3 divided by 0.1 multiplied by 100. So what we have is basically 1.3%. Relatively low. And that's what you have as the percentage dissociation in that case. Question 9. Consider a weak base like NH3 in water. Write the base ionization constant Kb expression. So a weak base NH3 is basically supposed to gain a proton, of course. So dissociation in water, so let's show that, plus water, so it's going to gain a proton. The water is going to become an hydroxide. So this is in aqueous state, the water is in liquid, aqueous, aqueous. Okay, so write the base ionization constant. So our value of Kb in this case is going to be dependent on NH4, the ammonia multiplied by the hydroxide, divided by what? Divided by the NH3. So water doesn't appear because it's in liquid state. We only show what is in aqueous and gaseous state. So that is our expression. Then the other part B says write the equation to calculate the pKb of this base given above. Okay, so how do you get to find the pKb? So basically when you're talking about the pKb, so your pKb value is basically equivalent to the negative log of what? It's basically equivalent to the negative log of your Kb. So it's basically going to be the negative log of this. That's what you're going to have. Okay, part C of the question says, using the above base dissociation process, show that Kb multiplied by Ka is equal to that. So we basically understand that for our pKb, we've said it's basically equal to the negative log of the Kb. Okay. So we also have to understand that pKa basically plus pKb is basically able to give us the negative log of Kw as well. Okay. So from that point, we also know that pK is also equivalent to what? Is also equivalent to negative log of Ka. Then we also know that pKb is also the negative log of Kb, and that's what we have in this question. So that is equal to the negative log of what? The negative log of Kw. So the signs we can divide by negative, they all become positives at that point. Okay. So from the laws of logarithms, we know that when you have an addition sign there, you can basically what you can do is you can basically get to, so we have an addition in between there. Okay, so we can factorize the log there. We have Ka plus Kb basically being equal to log Kw on the other side. Okay, so if we divide both sides by the log, what we are going to get is we have Ka plus Kb being equivalent to Kw. Okay, and that we've actually proven that, we've shown that. So from just the aspect of the pKb and the aspect of the pKa, which is supposed to be equal to the peak. So basically the argument has just come from this point where we are just trying to show that pKa plus pKb, this is equivalent to the pKw. So this is the negative log of that, negative log of that, negative log of that, which is still going to reduce to this part. Okay, question 10. So the pH of a sample of gastric juice in a person's stomach is that. Calculate the POH. So we've been given the pH already. So this is straightforward without even wasting time. So we say the pH plus the POH is basically equal to 14. So if we've been given the pH, our POH without wasting time is going to be 14 minus 2.1. So get your calculator there and plug in. Our value of POH, 14 minus 2.1. Basically what we have is 11.9. So we found the value of POH. The second part is the concentration of the hydrogen. So we know that basically when you're talking about the pH, it's basically the negative log of the hydrogen concentration. So we know that our pH is basically equal to 2.1. So a negative log of the hydrogen concentration. So we can divide both sides by negative. We have negative 2.1. Okay, so then this will become positive. So we know that the log that we're using has got a base 10 there. So the hydrogen concentration is going to be 10 raised to the power of negative 2.1. And what will be that? So 10 raised to the power negative 2.1. Negative 2.1, 10 raised to that power. So what I'm getting is basically, okay, let me punch that again. Okay, so what we are trying to find is now 10 raised to that power. So 10 raised to the power of negative 2.1. Okay, so what I'm basically getting is the hydrogen concentration to be equivalent to 7.9 times 10 to the power negative 3. So what is our concentration of the hydrogen ion? Okay, so the same concept can apply even as we get to find the hydroxide concentration. We're going to work with the value of our POH that we found. Okay, so we know that our POH is basically the negative log of the hydroxide concentration. So I can create some space there. So don't forget that our POH is basically 11.9. So what we have as our POH is 11.9. So negative log of the hydroxide ion concentration. So we can divide by negative, that will become positive, that will be a negative. So therefore our hydroxide ion in this case is going to be 10 raised to the power of negative 11.9. So negative 11.9 as our power. What I'm getting as the hydroxide concentration in this case is basically 1.3 by 10 to the power negative 12 molar concentration. So we've answered that now. B says the pH of 1.0 by 10 to the power negative 2 solution of cyanic acid is that. Calculate the Ka. So it's a different question on its own, standalone question. So what we've been given is the cyanic acid, which is HOCN. So we've been given its pH to be 2.77 at 25 degrees Celsius. Calculate Ka for that. Okay. So when this dissociates, it's basically going to give us that and that. So the initial concentration has been given to be 1 by 10 to the power negative 2 molar concentration. They're asking us to find the value of Ka. So we basically know that the value of Ka is going to be the constant of this reaction. And we made the point to say that our value of Ka is going to be dependent on the equilibrium concentration. So for this side we say this x times x, which is to be x squared. In this part we say the initial concentration. Okay, so that's what we have. Okay, so we're trying to find the value of Ka. What is going to help us? So remember you've given us the pH here. So we understand that pH is basically equal to the negative log of the hydrogen concentration. So we're able to find the hydrogen concentration, which is represented by x there. So basically our hydrogen concentration is going to be, so remember we said you divide by a negative on both sides, that will become positive, that will be a negative. Then where there's pH, we're going to put 2.77. So the concentration is basically going to be 10 to the power negative 2.77. Therefore, our proton or our hydrogen concentration is going to be 10 raised to the power of negative 2 negative 2.77, which is basically a 1.7 times 10 to the power negative 3 molar concentration. So we have our concentration of the hydrogen ion there. So that is basically our value of x, and we can plug in at that point where it is x squared. So we have 1.7 by 10 to the power negative 3 squared. Okay. Divided by 1 by 10 to the power negative 2. So therefore our value of K in this case is therefore going to be equal to 2.88 by 10 to the power negative 4. Okay, so that is the value of K in this case.
Are you enjoying this video lesson? So you can actually access the entire topic you are watching, or the entire practice questions of a video that you may be watching right now. So for example, if you get to check right now, these are full videos which shows member only content. So for example, this trigonometric tutorial sheet is like 5 hours 48 minutes. There are other tutorial sheet solutions and other topic videos available fully here. You can see the hours that they are. So on YouTube, the ones that are available for free, just like maybe half of that, or even just a third of the total time, all these tutorial sheets, you have access to them. So this is actually available in all the courses. For example, you can see chemistry as well, stoichiometry 4 hours, atomic structure. So these videos, you can access them in 3 different ways that I'm going to show you. So if you go to our website is transcendedinstitute.net. Okay, so that's our website. So this is what we do. Of course, Transcended Institute, we just make tutorial videos. So depending on your location, there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. Okay, so you can also download our mobile app. The link is here. If you're on Android, I believe by the time you may be watching this video, even the iOS app may also be available. Okay, so alternatively, you can access the videos using our learning portal. The link is learn.transcendedinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you like learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets, which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course, this applies to all these other topics that are available. Trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So you can actually just head to the site to check the topics that are available at the time you're watching the video. So for example, I can show you work. These are videos available explaining work, including the tutorial sheet based on work. Okay, let's say you're interested in circular motion. These are videos available on circular motion with tutorial sheet solutions. Linear momentum. So if you watch these videos, trust me, you should have understood the topic in full. For example, momentum, this is what you get to learn. Check the length of the videos, and I mean they are. And then I can show you now a bit of some chemistry. So if you open chemistry, these are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the tutorial sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally, biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel.